I'm not going to be able to cover everything that Stan implied I was going to be able to cover, because I really want to focus on the gravitational wave signatures of core collapse supernovae. But I will, in the first half, talk about some of the new breakthroughs, I think, in the modeling of core collapse supernovae. I will say that the community collectively is now getting explosions most of the time. We're starting to agree on various details, and we understand, I think, and there's an emerging understanding of why there have been differences between the groups. But I won't be able to go into all the details, and I'll leave it to questions and behind-the-scenes discussions to fill in the gaps. I want to give credit, of course, to collaborators, in particular David D'Artagnan and Davide Radice for the simulations I'm going to show, and to Victoria Morozova for her wonderful work on the gravitational wave signatures. But there's also Aaron Skinner and Josh Gomes to thank. I thank the funders, of course, and since it's being taped, I thank them profusely. One of the things that we've been able to do is develop a new code capability, FORNAX, that can do these simulations in 1D, 2D, and 3D, and I'm going to show some 3D results today, where we do multi-group radiation hydrodynamics with approximate general relativity, but a lot of other things are not approximated. One of the limitations is that we do not do multi-angle transport. That would be the 7-dimensional problem that no one is able to do at this stage. But we're getting very close to being able to simulate with great physical fidelity the phenomenon, which we know has to be multidimensional, because these things are unstable. The neutrinos that come out copiously drive convection. There could be significant rotation, etc. So it's a very complicated problem. And as Stan did imply, the initial models are crucial to this. There's a mapping between the initial models and the final state, given chaos and turbulence as well. Don't look at any of these details, but the important thing with this FORNAX code development is that it's now explicit radiation hydrodynamics. We realize that the core of a neutron star, or protoneutron star, has speed of sound that's very near the speed of light. And so we didn't have to use the very complicated radiative transfer techniques associated with the implicit approaches. And doing it explicitly allows us to do it at higher order accuracy and 5 to 10 times faster in 3D. Than in the past. And so one of the major developments, and these are equations, there's a complicated grid, the code paper is going to be coming out in about a month on the basics. It has a lot of details, I'll leave that out. And we of course do lots of simulations, etc., to show that we can reproduce some of the classic tests and some of the more complicated ones as well. But one question that people ask is why different groups have actually come to different conclusions. And in fact, I think that things are converging. It's not merely because we've been talking to one another for such a long time that one has to start converging, but that we've been able to, because of the improvements and the capabilities of the computational architectures available, we can make mistakes fast. 1D is a solved problem in many respects, given the microphysics. 2D, usually in the past, took a few months to do a 2D simulation, and so you could have all sorts of disparate results without really exploring the parameter space. And so your own intuition was not very well developed, but you did publish papers. Now the 2D is basically a solved problem in many respects. There's still going to be chaos. But we can do 50 2D simulations for a second or 2 seconds. And so we get an intuition, we develop the basic systematics that was inaccessible in the past. And now it's 3D that is going to be approached as we did 2D 10 years ago. Again, there are lots of details here. This will be on the slides that you can look at later. But I want to mention a couple of things. The flow is chaotic. Not only are the initial models chaotic, as Stan indicated, and it makes perfect sense, but the initial conditions, the initial perturbations, for example, in a turbulent flow will give you final states that are different for the same, in quotes, initial conditions. So a 15 solar mass star with the same metallicity, without any rotation, in nature will explode differently. We don't know what the distribution function is, and that's really the goal of second generation theory. We're also not using the so-called ray-by-ray approximation. We're doing full multi-D radiative transfer, and most of the calculations in the past have been multiple 1D radiative transfers in the 2 and 3D context, and that's introduced artifacts which we publish and is generally agreed to. There are a few groups though that are doing full calculation. People at MSU, for example, Tataki's group in Japan, our group, of course. And so I think we have an emerging capability to actually simulate these things fairly sensibly. The equation of state is relevant, some form of general relativity. I will say from the outset, we're doing approximate general relativity. To do full GR with the full transport, nobody's done. So we're evolving to this, but it's much more sensible. There are many neutrino matter interaction effects. It's a very rich subject in nuclear astrophysics and particle physics, and we have to try to understand that. But this is still MEV physics, it's not TeV physics. There's still, we think we understand the basic neutrino matter interaction. It's a matter of the equation of state plus the interactions that's relevant. This is a heartening plot. This is a test problem that O'Connor put together where everyone did the same 1D simulation. They were just told what physics as you include. We didn't, but we're using very different approaches. And these are the neutrino luminosities for the different colors, for the different codes. And there were 6 codes involved. These are 4 of them. And again, our code is FORNAX, this orange curve. The fact of the matter is, and the anti-electron neutrinos here, the electron neutrinos are here, and I think that they're fairly close, despite the fact that they use different resolutions, different energy griddings. There's quite a number of differences. We didn't try to make them similar. The other thing is this curve here is for all 4 curves. It just are all superposed, which was quite surprising. There are differences, but there are something like 7% differences. And so when you say that the groups are getting different results from this perspective, you haven't been reading the literature, or certainly haven't been keeping track. However, those differences can translate into mean shock radii and the radius of the shock. A mean radius of the shock is a measure of whether it's exploding. If it's small, like 150 kilometers after bounce, I'm assuming people know the basic background of this subject. Stalled shock has been a problem. We've been trying to revive it ever since, and the Wilson paradigm has been what we've been really exploring with greater complications. Well, this is not exploding here, but these then explode, explode, and explode at different times. This is the same mass model, but using different microphysics. So what we see is when you're near criticality, when you're near the explosive condition, that little things make a difference. When you're far away, big things don't make a difference. Now, when you're far away in 1D, when you basically almost always don't explode, but as Stan indicated, there's a small set of lowest mass objects that do explode in 1D, although they're going to explode in multi-D because they're still unstable. Under those circumstances, most of the 1D calculations, you can change the neutrino matter interaction by factors of 2 and 3 and not make any difference. But it's 10%, 20% differences that can make a qualitative difference, explosion or no explosion, when you're near criticality. And that's what multidimensional effects do. It makes it much more close. So you have to do some of these things a little bit better. Many-body effects, what initial perturbations, etc. You can get Newtonian models to explode. It's not just general relativity. This is an example where different groups, and this is the Garkin group, the dashed curves are for 4 different progenitors, 12, 15, 20, and 25 solar masses from Stan's 2007 publications. They explode in these various places. This is time after bounce. 200 milliseconds, 400 milliseconds, 600, etc. The solid curves are our same models for the same progenitors, but they explode at different times, and that reflects that there's a sensitivity to the details. That we're actually getting the details about the same, but now we have to do it that much better. However, we're generally getting most of the models to explode. Now, I will say that this blue line, for example, and this is also recapitulated in the work of O'Connor and Couch, that this 12 solar mass model is harder to explode than the 17 or 20 solar mass models in this suite. So there's also a non-monotonicity in the compactness parameter dependence of the explodability. The lowest mass ones explode fairly easily. You go up in mass a little bit according to the progenitor suite that we've inherited, like the 12 solar mass, and it's harder to explode. And then as you go up in mass even more, it's easier to explode. Now, when you're up in very high masses, it's easy to explode early, but the binding energy that you have to overcome, the outer envelope, such as Stan showed, that the low mass versus the high mass density profiles, that becomes quite difficult. You have to overcome a couple of betas, or just one beta, which is 10 to the 51 ergs. And you may not have the energy to do that, it could fall back. And the simulations of the first second might indicate that a 18 solar mass star will explode, and you stop the calculation, but then you have to really carry it out further. So it's subtle. This is just an indication of the dependence on the microphysics. This is 2D simulations, and this is with the many-body correction, which I'm not going to go into in detail, but it's one of the corrections. And you see it starts to get vigorous earlier. They're otherwise the same, so you really want to get this physics correct. And you notice there's some sound waves coming out, which is generic, but not necessarily determinative. So the upshots, again, are there's chaos not only in the initial models, but there's chaos in the outcomes of these simulations. And that turbulence in this context, which is generic, it leads to some degree of unpredictability. So we really have to get the ensemble. However, and then so-called Mazurik's law is violated, which was developed in the 1D context, where you have nothing you do makes any difference. Things that you do now make a difference. But generically, or most of the time, you get explosions, and some of the explosions can be fairly early. These are exploding models, and you can see the range of masses here. This is just an example sweep. And this just shows, again, these are 2D simulations just to give some foretaste, but you can see how they explode. They can explode up or down or whatever. I will say that the so-called standing accretion shock instability can be seen at times, but it isn't really determinative of the mechanism. It's neutrino-driven convection. The so-called SASE does not generate much entropy. It doesn't really involve much energy deposition. If you didn't have the neutrinos, it couldn't explode no matter how much SASE you might have. It's neutrino-driven convection, the classic convection. And in 2D, you exaggerate the effects. You see the sloshing up and down. It isn't necessarily the so-called standing accretion shock instability. It's neutrino-driven convection, although sometimes you do see this SASE instability. And trying to piece that out is something important to do. As Stan emphasized, the progenitor models are crucial. And this is an example of the variation over time and from group to group of what a 15 solar mass model of solar metallicity might look like. This is the density profile. This is 10 to the 10 grams per cubic centimeter in the center. That's the Chandrasekhar core, just starting to collapse. This is the mass interior, 1.5 solar masses, 2.5 solar masses. And you see this variation. This is for the same progenitor mass, ostensibly the same metallicity. So these things need to converge as well, but whether it's this or this makes a big difference. And this emphasizes the point that Stan mentioned as well. We did 2D simulations for the new models by Tug and Stan at 15 solar mass, at 14.9 solar masses, and we're finishing 15.01 solar masses. The 15 does not explode. The 14.99 does. And this is the density difference. And the major thing is the sharp declivity in the density profile here. This is the silicon oxygen interface, where the entropy jumps, that entropy jump of 4, for example. And those differences made this difference. And you can see that they're fairly proximate in mass. So there is something to be said about what Stan said. If in fact his models are correct, there is going to be a variation in the outcomes that is not so easily mapped to the progenitor mass. And it lends a richness to the subject. It's one of the reasons that nature constantly confounds us and is something worthy of study and worthy to do battle with. Because nature always wins, but sometimes you can actually play the game with. Nature is difficult. The question is also whether the seed perturbations in this convective progenitor structure, where you have perturbations in the velocity, which can seed the instabilities, are relevant. This is an example. We put in some perturbations artificially here. This didn't have any perturbations, it was just off the grid. And you can see the different variations. This exploded earlier, although in this particular incarnation, they both were fairly late. You can see this bouncing up and down. That is not the SASE, that's actually neutrino-driven convection. Yes, there you go. Okay. And you can see the keratin explosion. This didn't explode until much later. This emphasizes the binding energy penalty you need to pay when you go up in progenitor mass. It's not completely monotonic, but mostly. 15 solar masses, 20, 25, 40, 60. And you go up here, if you wanted to have a neutron star left behind at 1.5 or a little bit higher solar masses, you have to pay this penalty. And you see from this model, for example, it's 2.5 betas. This is unlikely to explode, and that's a 40 solar mass model. These plots are important in determining the mapping between between what the models and what happens. So here's some, so let's just get an example of the differences between 2D and 3D. 2D is almost a conquered problem now. We've gotten a lot of intuition, and many of the models explode. 3D, number of groups have started generating them. Nobody's really generated a definitive calculation. They either use this ray-by-ray approach, or they change the microphysics, etc. But we're starting to get things that are interesting. This is the 2D simulation. The corresponding 3D simulations don't look like they have this axis effect. This is Sean Couch's way of emphasizing 2D is like this. It's a dowel. 3D is like this. You can use your imagination for that, but they're certainly very different. This is what we could do. This is what we can now do. This is an example of 3D simulation where we do just a slice. And again, you don't see the axial sloshing. When it does explode, it chooses its direction. It takes a little time in this particular case. In fact, most of our new models are not taking that much time to explode. You can ask about that. But you can see how it does explode. This is 400 kilometers and it's moved off the grid. These are nice 3D simulations from the Oak Ridge group, and this is from Max Planck. This is something we did a while ago, which has simple neutrino physics, not as complicated as what I'm going to show. But I want to show the following. You get this broiling and boiling behavior. That blue line there is the shock. But you naturally, in these contexts, produce the neutron star, which emerges in the center. And that neutron star can actually be rotating slightly, even if it didn't start rotating because of the transfer of angular momentum during that process. So new simulations, again, with these collaborators. I'm going to go through this quickly because I want to get to the gravitational wave results. First, I want to show that in 3D, when you change the physics just a little bit, and this is just a little bit different physics than this, and this is low-resolution simulations, just to make this comparison. The shock radius here that you achieve, just because you included a bit of physics that's not included here, is quite different. So it's starting to make a difference. This model exploded later. Okay, we start out with a perturbation, L equals 2 perturbation, and that actually was the axis. So we did it off-side just so we can show something. And this started to explode fairly early. You notice you get, first it has low L mode bubbles and boiling, and then it goes to lower L mode still, and you get dipolar and quadrupolar structures. This is going out to 2,000 kilometers in this movie, but this is the character that we have. That's the inner protoneutron star. And this started to explode only about 140 milliseconds after bounce. In fact, when we compare the 2D and the 3D, they explode about the same time. In the literature, there's some suggestion that the 2D is easier to explode, and that has been true in the past, but it doesn't seem to be true now. Now that did start with initial perturbations, which were fairly large. And so the initial perturbations from the progenitor structure are important, but not determinative. That was 16 solar masses. The gravitational radiation, though, and again, this work was led by Victoria Morozova. Wonderful job. There are all sorts of things in the literature about the rotational spike, protoneutron star convection, inner protoneutron star convection, the neutrino component, Christodoulou memory, or something like that, being signatures. And people can look at the details. I'm not going to go into every single detail here, but I want to show some of the general results. There's a lot of history to this, and this is just to give credit to earlier work of people who did the data analysis as well as theoretical work, and this could be doubled or tripled in length. But there was pioneering work done by Eva Muller, mostly focusing on rotation. What we see now is that rotation is the most crucial aspect. Now this is a Mull-wide projection of the accretion onto the protoneutron star. And the blue is high accretion rate and the red is low accretion rate. The point I'm trying to make here is that the accretion plumes that are hitting the surface are coming in from all directions. And it's those plumes that are causing the protoneutron star to excite in its fundamental modes. This is astroseismology. And that is giving us one of the dominant signals in gravitational wave detectors. The characteristic frequencies, as a function of time, can be predicted even with 1D simulations by and large. And they are universal in all the models. For a given equation of state, we get the same spectrograms. The magnitudes of the signals are different, but the frequency-time behavior is fairly similar. This I just like. This is the neutrino luminosity that corresponds to that. And you can see how it varies with angle quite a bit. This is the electron neutrino luminosity, the anti-electron neutrino luminosity. We're doing full 3D simulations to do this. And there's a lot of interesting rich behavior here that has to do with kicks. It has to do with the crystal dual-like memory from the gravitational waves off the neutrinos, because there's a lot of mass energy there, and they're carrying away that energy at the speed of light. These are example signatures. These are just H's, or H's times D's, in centimeters for different models. This is a rotational signature for that model. So you put in a little bit of rotation. There's an early burp right there. This is an integrated spectrum. There's a lot of detail here, but I want to emphasize two things here. One is, if you have gross asymmetries in the ejecta, you have matter memory, where the H is a permanent displacement. You also have, if you have asymmetries in the neutrino ejection, you have neutrino generated or neutrino source gravitational waves. Those are at low frequencies between 100 hertz and 1/10 of a hertz. Really 100 hertz to 1 hertz. And they, in the H values, dominate the signal, but not in energy. This is low frequency. We also have, so here's a comparison. Here's one model without rotation, here's one model with rotation at the spectrogram frequency. This is 1,000 hertz. This is 0 seconds to 1 second. And that is the characteristic F mode that's being excited by the accretion plumes hitting the surface. And this you see in every model. The development versus time is basically universal. This is the rotational signature in this figures, and that is the associated frequency. You can see what the rotation is doing for this particular initial rotation rate, and you can change this all over, but we just showed generic results. So the fact that there is significant stochasticity here, and there's not templatable, is belied in some sense in this space by looking at the frequencies that dominate. This is an old plot that shows just the rate rotational variation. If you have a rapid rotation, the signal is weak because you have a centrifugal supported bounce. If you have no rotation, the signal in the rotational context is weak. It's an intermediate rotation that has the maximum effect. I just wanted to say that. Let's see if I can do this. Shouldn't be able to. There we go. All right. We can sonify this. This is in real time. And you're going to have to hear the last one. Okay. We didn't do any Doppler shift to that. That's because this is hundreds of hertz to 1,000 hertz. The ear can hear this. And if you notice, that is the rotational signature. I can play it later for people who are interested. So you get these different behaviors, but did you hear the increase in the frequency? That's due to the fact that the core is shrinking inexorably in a predictable way. So when you get this type of behavior, that's that frequency right there. There's all sorts of other behaviors. There's interesting sourcing for this. When you get big signature, it's because you can see the reflected effect in the behavior of the shock wave that modulates the accretion, etc. So there's a correspondence between the hydrodynamics and the magnitude. And this is directly connected to the accretion that's hitting the surface. Now, there was one thing that's fairly interesting that we discovered, which is there's a gap there. Nobody's seen this before. We're not absolutely sure it's real, but we can't figure out any other reasons. And the reason we think it's physical is because we can reproduce that trajectory physically. And that is coming from an avoided crossing in the modes of the excited neutron star due to the presence of a trapped G mode in the center because of the inner convection. An inner convective zone gives you a trapped G mode because G modes can't propagate in a convective region. And if you excite a mode in there, it has this type of a frequency dependence. It starts out a little bit above a kilohertz and then goes down. This is a prediction. If you see this, which is going to be hard, if you see this behavior, you have a direct signature of the interior convective zone that has been predicted for a number of years. It's directly connected to theoretical progress. And you can do this with the avoided crossing analysis. This is just quantum mechanics. When you have modes that have the same quantum numbers and start approaching in frequency, they repel. You can read this in Beta from 1920, in the 20s. You can also look at the equation of state dependence, and this is nice work by Richards et al. This is only in the first 20 milliseconds, though, but the equation of state dependence was fairly weak for the rotational signature. However, if you look at the later times, these different curves, and we had to identify them by the analytic model for the development of the frequency versus time, you change the equation of state a little bit, the frequency development is different in a predictable way. And this type of behavior can give you priors that you can use in the signal extraction in the next generation of detectors, and perhaps, if we're lucky, in this galaxy with the current generation of detectors. Voyager, for example, certainly A-like. Other groups are seeing this type of behavior too. There is a little aliasing and things. We dump this every 16,000, at 16,000 hertz to be consistent with the LIGO capability. So there's no aliasing in this at all. If we do this in 3D and compare it to 2D, and a number of groups are getting this, the 3D signatures are a little bit weaker than in 2D, which may not be good, but the frequency dependence, the spectrogram is almost exactly the same. And that's almost exactly the same. They just calculated that here. You see that line there? That line, that gap, and that void in there are exactly the same in the two cases. This is the 3D, this is the 2D. Other groups, such as the Oak Ridge group, have a red curve in 3D and a blue curve in 2D, and there are differences there that have to be cataloged. We can now do a 3D simulation modulo the queues in the supercomputer centers about once a month. In the past, it was once a year. And so there's been great progress, I would opine, in this subject. And one of the signatures is not only neutrino signatures, which I'm not going to talk about, but the gravitational waves. And so this is a summary, and I thank you very much for your attention.
Burrows. So Adam, what if I can make this quantitative for the signal? Supposing you can take a large enough volume to get one event per year. What characteristic H value are you getting for a gravitational wave detector?
I was going to ask the same question.
Okay, I will say that it's going to be very difficult for these objects to be seen outside the galaxy. So the rate is small. I will also say, it's not your question, but I want to emphasize this, that in fact, the neutrino data may be very useful, and a co-analysis of neutrino data with gravitational wave data will give you more than either one of them. The neutrino data, at the very least, can tell you when it happened, but they can also tell you how quickly that core shrank, because it's the neutrino losses that are causing the core to shrink. If you can get that out already, then you can say something about the equation of state using the gravitational wave data, just as I showed, because you can correct for that. There's more that can be done. There's no paper that's been written on this subject.
Yes.
Adam, do you understand why the 3D simulations give weaker gravitational wave signatures than the 2D?
Yeah, the 2D has the artificial character of being a ring falling into this. And that ring has more inertia. It's harder to break up. In 3D, when you have a creta, that material can break up by Kelvin helmets very easily, and then you have more of a chance of actually ejecting that material. That's one reason 3D explosions are a little easier than 2D, all else being equal. 2D are easier in some sense because you have the cascade of large scales, and large scale turbulent pressure is helpful. But those two things together sort of cancel. And there are other aspects as well that are being worked out, and we can talk offline about that.
One more question. Yes.
So I realize, of course, that, as you said, rotation is a challenge, but how close might we be to having an idea of how well preserved the angular momentum would be during a supernova that forms a black hole?
That's a difficult question. Rotation, I haven't mentioned in great detail here. We have models of rotation. The effect of rotation on the explosion is probably non-monotonic. Low rotation doesn't make any difference, intermediate rotation helps, and large, fast rotation hurts. But we don't know what the rotational profiles are. As Stan has done some calculations with Alex Hager, trying to look at what the evolution of the rotational structures are. Other people, such as Maynard's group, has used a different approach. They try to get those, but the actual evolution to the final rotating state has not been resolved. And it is rather crucial. So my own personal opinion is, and this is consonant with what Stan had mentioned earlier, is that low metallicity without significant mass loss retains a significant amount of angular momentum. And so it's those objects that will, in principle, give you the reservoir of angular momentum. But there are evidently processes, and there are papers by Cantiello and a whole set of people now, there are evidently processes in stars that have been defined by astroseismological inversions that actually lead to slower rotation in the cores of stars than people would have predicted, for example, with the Sprott-Taylor dynamo. And so we really don't have a good handle on the rotational evolution of massive stars, or any types of stars. My own feeling, though, is that it has to be low metallicity to get significant rotation to get the collapse star model, which I think is the preferred model for those types, that class of gamma ray bursts. Beyond that, I'm not really prepared to say how the rotation would evolve after given an initial rotational profile, but I will say if it's rotated really rapidly, there's no way of suppressing magnetic field generation, and magnetic fields coupled with rotation will also spin down the thing left behind. And we've seen spin down in models where we had 10 to 15 Gauss fields with rotation rates for 2 millisecond periods that spun down the core rotation by a factor of 2 in 30 milliseconds. The early spin down can be quite fast, but I'm being ushered out, so we can talk offline.
Fast spin down. So let's thank Adam again.